Today we're starting Unit 3 with exponential expressions. I want to make sure that you remember about common ratios and how that relates to exponential functions or expressions. So a function is exponential if there is a common ratio. So to check this from a table, note that the x values have to be in order, increasing by 1. If there is a common ratio, then we can say the function is exponential. So when we look for a common ratio, if you recall, we do that. You might remember my crooked arrows, right? We always start at the bottom or the end of the table and do 324 minus 108, or sorry, 324 divided by 108, and then 108 divided by 36, and 36 divided by 12, 12 divided by 4. We use a fraction bar for division. It just helps us write it short. If we get the same answer every time, it's called a common ratio, and that means that it's exponential, the function. This works here too. You can get whole numbers, you can get fractions, you can get decimals. If it's a match by dividing, working from the end back to the beginning, y values only, then we're saying that is the common ratio and the function is exponential. So now I'm going to show you how we'll use that common ratio in an exponential equation. Before we look deeply at exponential expressions, I need to make sure that we're speaking the same language. So the notation and what each piece means is important. When we're looking at a term with an exponent, the exponent part is raised up as a superscript. The value of that tells you how many times the base gets multiplied by itself. For example, 3 to the power of 4 means 3 times 3 times 3 times 3. 3 times itself 4 times, and you would do the math and write the answer. 3 times 3 is 9, times 3 is 27, times 3 is, I can't even think of it off the top of my head, but you get the idea, right? Okay, so the bottom number, often signified by a b, is called the base. And that can be a number or a variable. So you could have x to the 5th, and you already know that means x times itself 5 times. All right, base, exponent. An exponential expression is an expression with at least one term that is a constant raised to a variable power. A constant just means a number, any number. An exponential expression has the variable, usually x, but not always, in the exponent. So there can be a term that is just a number. There can be other variable terms. For instance, this last one has an x being multiplied to the 2. But if the expression has an x in the exponent, like each of these, even if something else is happening to it, we call it an exponential expression. So we often use exponential expressions in a function, an equation that you can put in Desmos or evaluate for different values. So the basic exponential function looks like this. Y equals a times b to the power of x. Here's what this means. A, the number in front, so not the base, not the exponent, but a number in the beginning being multiplied to the base with the exponent is called the initial value, sometimes starting value. And that will also be your y-intercept when you graph this function. So that's really convenient to know. As you already heard, b is the base, and this is going to be the growth or decay factor. You'll hear about that in a minute. The exponent, often just a plain x, sometimes a t, usually refers to some unit of time. It could be in hours or days or weeks or years, but it generally refers to a unit of time. This is what an exponential growth function looks like. And this is what an exponential decay function looks like. So notice for a growth function, if you read it from left to right, it's kind of going uphill. It's a curve that goes higher as I move to the right. Whereas decay is also that same curve, but it starts higher and goes down, decay, the farther you go to the right. You can tell if an exponential function is growth or decay just by looking at the equation that you're given. That b, the base, is your growth or decay factor, and it's your clue. If the value of b is bigger than 1, you see it right here? That tells you that this is a growth function, even without graphing it. If the value of b is between 0 and 1, so a decimal or fraction that's between 0 and 1, then it is a decay function. Let's do a couple of these together, and then I'm going to have you finish them on your own so that you can see if you're really getting it. There's a reminder up here in the upper right. Exponential growth is when b is greater than 1. Big, think of big numbers, growth. Small numbers, fractions, decimals, decay. The decimal has to be less than 1. Think about it that way. All right, so here my value of b, the base of the exponent, is 5. Bigger than 1, right? This means that it is growth. All right, look at the next one. Which part of this is our b? It's the base, the part that's being raised to the exponent. 0.75, that is less than 1. That is decay. All right, I want you to try the rest of them. Pause the video now and come back when you're ready to check your work. All right, how'd you do? Notice, bigger than 1, growth. Bigger than 1, growth. This number is smaller than 1, decay. And this number is smaller than 1, so it's also decay. All right, sometimes the equation isn't given to you. And so I'm going to show you that if you're given a table, you can use the initial value and the common ratio to write the function equation. So the initial value is the y value when x, which is usually time, is 0. So at the beginning, before there's any growth or decay, what is the value? And you'll see that right here when x is 0. Time is 0. So before there's any growth or decay, this is the value. That is your value of a. All right? Now, to write this, we need the initial value and we need the common ratio. And notice this has an R there instead of a B. That can happen. R I actually like better because it makes sense in my head. Common ratio, R. You've done it before. All right, so we start at the bottom or the end of the table, Y column, and we divide. 16 divided by 4, that's 4. 4 divided by 1, that's 4. And 1 divided by 1/4, that's 4 also. You could do it in the calculator to confirm. All right, that tells me that R is 4. So if A is 1/4 and R is 4, then this is how we write our equation. All you do is plug in your A and your R. You leave the X and Y alone. Let's look at how this works for a real-world problem. We have a scenario. Carlos bought a new toy fish that triples every hour when placed in water. Its size triples, apparently. Okay, is this growth or decay? They give us the equation. All right, they used function notation. You know function notation. That's the same as y equals. It's growing. We know this from two things. First of all, growth. It's tripling. That's getting bigger. It's growing. I can also look at the value of b. b is bigger than 1. And notice tripling results in a 3 for my growth factor here. So the growth factor is 3. And that's because of the tripling. All right, what is the 4? Well, 4 is our A, isn't it? What did that represent? That represented our initial value, which in this case is initial value. In this case, that's how many fish he started with. Number at the start or the beginning. All right, now I want you to graph this using Desmos, and you can use the M of t, or you can type y equals. Either way will be fine. We want to look at what part of the graph makes sense in the context of this problem. So I want you to pause the video and go ahead and put this in the graph in Desmos. Okay, so you see we have this growth curve on our graph, right? I typed it just the way they gave it to me, and while Desmos doesn't know some letters, it understands function notation, and that t is our x. So it does put this on here. But now remember, t was time, and our answer was how big or how many the fish were. The problem wasn't really clear, but it doesn't matter. Neither of those things can go into the negative. So what we're really interested in here is the first quadrant, only this piece of the graph. Think about what t is. T is our x. Time can't be negative, and neither can the number of fish or how big that fish is. Right? So we're really only interested in quadrant 1, the upper right region of the graph. While we're here, I want to show you how you could look at a table. So if you click the gear, you'll see a table option pops up. Create table, and look what you have. Desmos gives you x values, which is t, by the way. I wish it would write a t up there, but it doesn't. And y values, which in this case is m of t. Like I said, it's a little confusing. It knows that x and t represent the same thing. I wish it was more consistent. But what it's saying is if you plug in a 0, you get out a 4. Input, output. If you plug in a 1 for t, and do the math, you get 12 as your answer. Input, output. And you can add rows. If I want to know when it's 7, it tells me the answer. And if I want to change one of those because negatives don't apply, I can put in 6. Okay, so the graph will be what it is you'll have to determine whether it applies in that context.